So payload design drivers. There are different classifications of payloads, as we talked about earlier in class. For our CubeSats, I think the most relevant ones are observation, which many of you have chosen, communications or navigation, and in situ. Observation payloads are self-explanatory as payloads that observe, typically through remote sensing. Here's an example of a passive and active remote sensing system, where the passive system uses some external source to create the light, whereas an active source will bring the light source with them, potentially at some kind of frequency that is specific to that subject. And then both systems have a sensor that collects that light that bounces back. Communication payloads, which you'll see over here. Communication payloads may be separated into unidirectional systems that gather information, or two-way systems that gather but also transmit information, like GPS satellites. Navigation payloads track and transmit position information, like the Global Positioning System, which is GPS, or software-defined radio platforms. And then finally, I'll talk about in situ. In situ payloads measure signals in the environment directly that cannot be remotely sensed, like magnetic fields, gravity, or sample collection. The sensor necessitates being in the probed environment to be able to capture the subject data. Here you will see a typical Fluxgate magnetometer. Magnetometers are really common, and their precision varies very widely. We have a very coarse magnetometer on our spacecraft that is in the form of a chip. But even Europa, for example, has a magnetometer that is very fine. Either way, magnetometers work in situ, where there's some external magnetic field, and then here is a Fluxgate sensor that has a sense winding and a drive winding that flows current when there is a magnetic field presence. There are constraints to payloads. So there are fundamental constraints, such as laws of physics that limit observation. Here is an example of the diffraction limits. If an image is made through a small aperture, then there is a point at which the resolution of the image is limited by the aperture resolution. As a matter of general practice in photographic optics, the use of a smaller aperture will give greater depth of field and a generally sharper image. So the image on the right here shows the effect of diffraction versus an idealized image. And this limit is particularly pronounced for objects with images that are very close together. Due to the diffraction limit, these images will blur together and be indistinguishable as unique bodies. And there's something called the Raleigh Criterion that specifies the minimum distance between two images so that you can uniquely resolve the two images. But anything closer than that, you won't be able to resolve. Okay, another constraint is technological, which specifies the ability of state-of-the-art detectors to measure the subject. So here, we are looking at the technological limitations of an image sensor. The image sensor must be cooled by a temperature control unit. Given the quality of this technology, the data could come back with more or less noise. Other sources of error or noise can be in the manufacturing of the LED, for example, or the current control board, or the optical fiber. Or it could be in the temperature probe's ability to feed back a sensible temperature. Other sources of technological error could be the manufacturing of this entrance slit, the mounting of these different optical components, or even the data resolution of the computer that is collecting and storing this information. This image on the left shows the technological limitation of observing light across the band of wavelengths. So this is the consequence of all the technology limitations accumulated into the final measurement. And then the final constraint I'll talk about is the mission constraints, where you have to adhere to size, weight, and power constraints due to the spacecraft design or launch vehicle selection. It could be that detectors or payloads may not be miniaturized any further without significant sacrifice to the mission performance, in which case you'll have to change the way that you do a mission or have to sacrifice for your payload. Our mission constraints are quite clear. So we have a CubeSat form factor in which the volume is constrained to 10 centimeters cubed. The mass is constrained to less than 1.33 kilograms. And then further, the kit is constraining the volume for the payload, which we've reserved for about 1/4 U. And then we've also dedicated about 50 watt hours for energy storage. And the question here, would NASA goal alignment also count as a constraint? And absolutely it would. So at the end of last class, I wasn't able to finish the payload requirements for observational payloads, but you can refer to this as just a generic baseline of the different factors that you have to consider when you're writing your subsystem requirements. So they come in general, mechanical, thermal, electrical, and subject-specific requirements. So I think we went over all of the mechanical ones. For thermal requirements, maybe think about the way that the payload needs to operate in thermal ranges. Think about the different mechanisms that you can use to control the temperature, especially the distribution across the payload. The temperature also affects the way that the structures expands or shrinks, so that may have to be taken into account. And then for electrical, you have to think about the power requirements of your payload, the data rate storage, the kind of command, control, and telemetry architecture that is underneath. So like what frequency you're communicating at and the amount of power that your antenna is required. Hold on 1 second. And then finally, for subject-specific things, if your observational payload needs an unobstructed view to the space environment, then you need to think about how that field of view is going to be achieved. You probably need to be mounted close to the edge of the structure and make sure that all kind of structures in the field of view are not obstructing the field of view, but also while maintaining structural integrity. Your payload may need some kind of pointing, stability, precision, or agility. So like the agility is how fast you slew or you're tracking some kind of motion. The subject might be sensitive to contamination. So that comes from environment testing. And then also your subject may need some level of autonomy or operations, which comes from a mission architecture. Yes. Okay. So some leftover questions that I'd like to address. There was a question about the resolution of KAO's camera. And I'll let the KAO team speak for themselves, but I believe they wanted to resolve the Hawaiian Islands. So if that is the ultimate mission objective, then you need to work backwards. to what level of resolution in units of meters or kilometers is necessary to resolve the Hawaiian Islands? What altitude are you flying at? And then given that, given a camera at that altitude, what kind of pixel resolution can you resolve? And does that meet the resolution threshold of the Hawaiian Islands that you're trying to observe? So maybe you also have been doing that with your payload requirements. I hope you have. And the last question is, with a CubeSat, is it more likely for the other subsystems to have more priority? And my answer is more open. So having a successful science mission is the ultimate goal. If it's required that the technology occupies a certain volume and that compromises with other systems like the payload, then that could be true. So a general trend is that as you scale down, some things don't scale as well, like we were talking about the batteries and the power board. So for our particular CubeSat design, I think that is true, but it's not necessarily the case. You could have a CubeSat design with different components that does scale well and will incorporate a larger payload, for example.